Hello, this is Tyler Beamer, math instructor at Haywood Community College. This is an instructional math video for Math 272, Calculus 2. In this lecture video, I want to show how to find the area between curves. This is Chapter 6, Section 2 out of our calculus book, titled Region Between Curves, and I'm going to show some of the definitions out of the book here and work out some problems so that you guys can get a good understanding to begin your homework assignments. Alright, so this idea of finding the region between curves actually stems from the idea of Riemann sums, which we talked about in Chapter 5. And the book does a good job of giving some visuals here. Let me just try to work on this to get a good picture. Okay. Alright, got a little bit of a glare there. So in Chapter 5 we talked about the idea that integrals allow us to find the area between a curve and the x-axis. And of course we first looked at Riemann sums, and Riemann sums is this idea that essentially we fit a whole bunch of little rectangles in here in between the curve and the x-axis, find the area of all those rectangles, and then add those up. Now, of course, that gets really tedious, and so we obviously want to work away from that, but we want to have a conceptual understanding of where these definitions and formulas that we're going to use are derived from. So let's do that now, and I'm on page 412, just so you guys can kind of follow along in the book. And then also watch the video. So remember that delta x essentially gives us the width of the rectangle. A and B is the starting points of our region. So I'm going to shift back over to this graph here. Notice that A is the leftmost ending boundary point for the shaded region, which is located here. B is the rightmost boundary for the shaded region between the curves. So that's kind of like the stopping and the starting point in terms of the x-axis as to the shaded region. Okay, so delta x essentially gives me the width of the rectangles, so I basically take b minus a, which is the distance, the horizontal distance of that shaded region, and I divide it by n, and n is essentially how many rectangles I'm going to fit between those two curves. And so as n increases, we get more and more rectangles in here. The width of each rectangle reduces and becomes smaller and smaller and smaller, and thus we get a much better estimate for the actual area, and we saw that in Chapter 5 when we looked at Riemann sums. So the same idea is applying here. The difference is, right, we are able to find delta x, which is the width. That's not a problem. That's b minus a divided by n. The difference here is how do we find the length of each rectangle, right? So when the curve was, if we were finding the area of a curve and between the curve and the x-axis, right, that was pretty easy to find, right, because I could just essentially use the height of the curve, right? So, but in this case I have two curves, and I want to find the length or height of this rectangle between those two. So to do that, I actually take f of x, which is where the point is on the top curve, and I subtract that from g of x, which is the y-coordinate of where that point is on the lower curve, and I subtract those two, right? And so basically this gives me the y-coordinate for the top curve, the y-coordinate for the bottom curve, right? So then if I subtract those two, that gives me the height of that rectangle. And so when you see this area formula in the Riemann sum, let me focus in on this a little better. You know, we have the summation, which is summing the area of all those rectangles. This is the length of each of the rectangle, f of x minus g of x, times delta x, which is the width of each one of those rectangles. And of course, length times width, this is width, this is length times width gives me the area of each rectangle. And of course, once I find the area of all those rectangles and sum them up, that gives me an estimate for the area of the region. So that's the conceptual idea behind this definition, going back to, like I said, Riemann sums. Now, one of the most important things that we want to keep in mind here is that this needs to be f of x minus g of x, where f of x is the top curve and g of x is the bottom curve. That way, when I subtract these two, I get a positive value there. Since we're talking about length, it wouldn't make a whole lot of sense to say that a rectangle had negative length. So to get our sign right here, we want to make sure that f of x is the top curve, g of x is the bottom curve. Okay. So like we looked at in Chapter 5, we started with Riemann sums, and then of course that got really tedious, and then we said, hey, we can do this much easier with integrals, and so that's what we're going to do here as well. So here is our definition for the area between two curves. It is using integrals, and integrals is just an easy way for us to essentially add up all of those rectangles in the Riemann sums, and it makes it a lot easier for us. So notice that A and B is essentially the boundaries, the leftmost boundary and the rightmost boundary for the area region that we're trying to find. And then f of x is the top curve, so that needs to be the top curve. And then g of x is the bottom curve. And so when I subtract those two, right, that allows me to find the height or length of that rectangle. And then of course when I integrate that, I essentially am doing the Riemann sums where n approaches infinity, and I squeeze infinite number of rectangles in there, which gives me a much better estimate, and of course it's much easier for us to calculate as well. So that's the formula that we're going to use to find the area of a region between two curves. So we want to keep that in mind when we work out these problems. Alright, so let's look at an example. Let's look at number 5, and I am on page 416 now. That way you can kind of follow in the book. Alright, so notice I've got two curves, right, and the book does a good job of kind of color coding this so that I have the black line as being the line y equals x. Let me zoom in a little bit more here. And the bottom curve being x squared minus 2. And that's in red. And so we want to find the area between those two. So the first thing we need to do is to find what A and B is, right? So what is the leftmost boundary for the region between the two curves, and what's the rightmost boundary? So basically, this point here is A, and then this point here is B. So we want to essentially find that x-coordinate, right, for where those two curves intersect, and we want to find this x-coordinate for where those two curves intersect, and that way we know that our region is essentially going from here to here, right, in terms of the x-axis, right? So I kind of have a starting and an ending point for finding that area. Okay, so messing up my book here, but that's okay. Let's look at how to do that. Okay, so I'm going to shift to the good old paper and pencil here. Bear with me while I get all this situated so you guys can see. All right, and I'm going to label. So this is number 5 on page 416 so you guys can follow along. So I'm going to label f of x as y equals x, since that's the top function. And then I'm going to label g of x as y equals x squared minus 2, since that's the bottom function, and that'll keep us in line with our definition when we get to it. Okay, so like I said, I want to figure out what a and b is, and that's the intersection points. So to find that, essentially set those two equal to each other. All right, so x equals x squared minus 2. Right, I'm basically setting f of x equal to g of x, right? And so when they are equivalent to each other, would represent the intersection point on that graph, right? So notice we've got a quadratic here, so let's solve that quadratic, and to do that we want to set it equal to 0. So move the x over to get it in the standard form. And then we want to try to solve that by factoring. So the factors are going to be x minus 2 and x plus 1. Set each of those factors equal to 0 and solve. So x equals 2, x equals -1. So that's going to give us our a and our b, right? Our a, which is our leftmost boundary, is going to be -1, and our b, which is our rightmost boundary, is going to be 2. Okay, so let's shift back to our graph just to make sure this all is making sense here. If we go back to 5, just to have a sense of the graphical interpretation of a and b. Right, we know that this intersection point here is -1, and then this intersection point here is 2. Right, so the x coordinate of that point is -1, and the x coordinate of that point is 2. Okay. So that gives us essentially our starting point and our ending point for the definite integral, right? So that we can then evaluate it, okay, using the fundamental theorem of calculus. All right, so let's go back to my pen and paper here. So using the fundamental theorem of calculus and the definition of finding the area between two curves, right? This is the definition here. We've got an integral from a to b, which we just found, and we've got f of x minus g of x dx, right? And we have identified what f of x and what g of x is. Remember, f of x needs to be the top curve, and g of x needs to be the bottom. So essentially, I have x minus x squared minus 2, and I'm going to put that in parentheses just to make sure that I get all of my signs right here. Dx, and we know a and we know b. All right. So now we just need to simplify this and integrate it and use the fundamental theorem of calculus to actually evaluate so we can get an area. So distribute that -1 through. We get this. I'm just going to write it in a standard form. And then, of course, since that's a polynomial, It's not too difficult for us to integrate that. So we're going to add 1 to the exponent and then divide that by the coefficient. So we get negative 1/3 x cubed plus 1/2 x squared plus 2x, and of course that's getting evaluated from 2 to negative 1. So now we plug in our values here using the fundamental theorem of calculus. Okay, minus. So this is B and this is A. So plug in A here. Just be careful with your signs. Okay, so then when we evaluate this, we should get 10/3 over here minus negative 7/6, and of course those double negatives are going to turn to positives. And then when I add those together, I get 9/2 positive. Okay. So then, what does that mean in regards to our actual problem here? So if I go back to the graph, right, the area between those two curves would be 9/2. So this area here is 9/2. That's what that's telling us. Okay. So that's one example. Let's actually take a look at the one right beside 5, which is number 6. Okay, and this one is slightly different. I'm still on page 4. Ooh, still on page 416. All right. So we've got two curves, and we want to find the area of both of these regions here. And combine those. And notice this problem's a little bit different because it switches as to which curve's on top and which curve's on the bottom. Right? So the red line is the function y equals x cubed, and then the black line is the function y equals x. And so when we're down here, from here to here, the top function is actually y equals x cubed. And then after that, it switches, and the top function is y equals x. So because of that, we actually are going to find these two shaded regions separately and then combine them together. Okay, so we first, once again, need to find these intersection points because that's going to give us our values for A and B, essentially the starting and stopping point of those regions. So to do that, once again, we're going to set those functions equivalent to each other. Alright, so this is number 6 on page 416. Okay. So we want to essentially set, these are our two functions that we have. Y equals x. So to find the intersection points, we want to set those equal to each other and solve. So we get x cubed equals x. So once again, we're solving a polynomial, so let's set that equal to 0. Let's factor. All right, we can use the difference of squares here to factor the x squared minus 1. set each one of those factors equal to 0 and solve. So x equals 0, x equals -1, and x equals +1. So that gives us our intersection points. So going back to our graph, here is -1, here's 0, and then here's +1. Right? So we needed to identify those values of A and B, which were not given to us. Okay, so like I said, we're going to do this separately. We're going to find the area of this shaded region between -1 and 0. Then we're going to find the area of this shaded region between 0 and 1. Once again, we have to do those two separately because the curve that's on top changes. And then once we find each of those areas, we'll combine them together. So that's our game plan. So let's start down here. Let's find this area first, or we could just write it all out together. So the first area down below the x-axis is going from -1 to 0. Right? So we've got our a and our b there. And notice that the top function is x cubed. So that's our f of x minus the g of x, which in this case is the bottom one, which is x. So that gives us the area of that shaded region, and then we want to add that to the area of the shaded region above the x-axis, which is going from 0 to 1. And once again, it switches as to which function is on top and the bottom. So in this case, the function that's on top is x, and the one that's on bottom is x cubed. Okay. So that's something to keep in mind. All right, that's why we have to do this separately. So now that we've got that set up, right, now we can essentially integrate. So let's integrate each one of these, and we can use our power rule for integration since this is a polynomial. So we get 1/4 x to the 4th minus 1/2 x squared, and then that's going to be found from -1 to 0 plus this region integrated. Once again, we can use the power rule. So 1/2 x squared minus 1/4 x to the 4th integrated from 0 to 1. So we use the fundamental theorem of calculus here. So let's do this over here first. I'm just going to write everything out so you guys can see this. So plug in the 0 minus plugging in the -1. So just doing a definite integral here, which you guys have done numerous times. Okay. So this is obviously going to be 0 minus -1/4, and the double negatives turn to positive, so this gives us 1/4. Okay. So that's this side of the problem, right? So before the plus sign. So now let's do the other definite integral, plugging in 1 and then the 0. Whoops. Zoom out some. Okay. So this here is going to give us a fourth, and of course this is going to be 0, so 1/4 minus 0 is obviously a fourth. Put in all my grouping symbols here. Okay, and then a fourth plus a fourth is a half. So that is our area of both of those regions combined together. So that one is, like example 5, you just got to be a little bit more careful there because, the curve that's on top and the bottom changes. So I think they call that in the book a compound region. So if you see that or hear that notation or see that notation, you'll have an idea of what they're talking about. All right. Let's look at another example here. Let's look at number 11. Getting a little bit more complicated. So number 11 on page 417. All right, it says sketch the region and find its area. So we want to find the region bounded by 3 functions, and we've got some transcendental functions in here. Okay, so y equals e to the x, y equals e to the negative 2x, and x equals ln of 4. So yes, it's always important to get an idea of what this looks like graphically. You can obviously use your graphing calculator to give you an idea here, and that's kind of how I got a good sketch of the graph, is starting with the calculator. So I'm going to sketch what I have. So we first of all have y equals e to the x. So that looks like this. And this is a rough sketch. Okay. Y equals e to the 2x is actually going to look like this. Okay, so we're going the other direction with that one. Okay, so those two intersect at this point here, and we're going to have to figure out what that is here in just a moment. Okay, and then now your calculator is not going to graph this one, which is x equals ln of 4, because that's a vertical line. And I'm not sure that the graphing calculator can graph that. But ln of 4, that's just a constant. So you can calculate that, 1.386294361. So we know it's going to lie to the right of 0, and it's going to be somewhere over here as a vertical line. So this is x equals ln of 4. Okay. So just make sure that y equals e to the x, that's the curved line. Just want to make sure you guys can get that idea. Okay. So we want to find the region bounded by all 3 of those. So that's this region here. So alright, so that's the graph, and that's helpful, right? Now we still need to find the A and the B. So, once again, the A is the leftmost point, so we need to figure out the x coordinate here, which is going to be A, which obviously is going to be at 0 on the x-axis. If we wanted to verify that, just to be sure, we could set e to the x equal to e to the negative 2x. to find that intersection point, because that's where those two curves intersect, and then solve that. And so using our properties of exponentials, since these have the same base, we can set the exponents equal to each other. Add 2x to both sides, and we get 3x equals 0. Divide by 3, and we get x equals 0. So obviously, looking at the graph, we kind of already know that, but just to be safe, to verify, we could set those equal. So that tells us that this point is at x equals 0. So that's our value of a, essentially. Okay, and then the value of b is pretty much given to us as well, because that's going to be this vertical line here. That's the rightmost boundary for the region, and that's going to be ln of 4. That's a vertical line. We know that it's going to go through ln of 4 on the x-axis. So this is actually our b. So we have our a and we have our b kind of given to us. We didn't have to do a whole lot of work to find that. All right. So now we've got to identify what the top curve is and what the bottom curve is, right? So in this case, the top curve is here, and that is, once again, e to the x. Okay, and then the bottom curve is here. That is e to the negative 2x, right? So then we can now do our integral. We have a, we have b. We know what the f of x and the g of x is. So our a is 0. Our b is ln of 4. We know that the top curve is e to the x. Bottom curve is e to the negative 2x. So we're going to subtract those two. All right. So now we need to integrate and do our fundamental theorem of calculus. Well, e to the x is pretty easy to integrate. That's e to the x, so that makes it nice. Okay, and then we would want to use our rules for integration to integrate this, since we have this coefficient up there of negative 2. So that's actually going to end up being negative 1/2 e to the negative 2x. So basically, this exponent's going to stay negative 2x, but this value here is going to come in front and divide by that coefficient, which is a 1 there. So we get a negative 1/2. And of course, we've got double negatives there, so that's going to turn to positives. All right, and then of course that's getting integrated from 0 to ln of 4. So we want to do our fundamental theorem of calculus at this point. So e to the ln of 4 plus 1/2 e to the negative 2 times ln of 4 minus e to the 0 plus 1/2 e to the negative 2 times 0. Alright, and so we get some kind of crazy fractions, decimals here when we work this out. We actually get 129 over 32 for this one. And, I'm saving some steps here by not working that out. But, if you know how to use a calculator, you can basically just plug that whole thing in, and it will also convert that to a fraction for you, just to keep it accurate. Over here, this one's actually easier because we know that e to the 0 is equal to 1. Anything to the 0 power is equal to 1. So that's going to give us 3 over 2. And then, of course, subtract those two numbers to get 81 over 32. All right. So that one, was a little bit more complicated, a little bit more involved. All right. And I will post these notes to Moodle as well, so that you guys can hopefully have as many resources as possible. You can have the notes, you can have the video. You can have the work, kind of compare everything together. Alright, what's the next one I was wanting to do? Oh, okay, so now the book switches to integrating with respect to y. So let's take a look at that. Alright, so when we're looking at integrating with respect to y, we're essentially changing the way these rectangles are drawn. So instead of the rectangles actually going up and down, when we look at integrating this with respect to y, stop. Sometimes this thing just takes off and doesn't want to stop. We're looking at essentially rewriting the function, right, so that it's solved for x, and of course that's going to essentially inverse everything. So these rectangles are now going to be going from side to side. Instead of delta x as being the width of the rectangle, it's delta y. And then of course we want to still find the length of that rectangle, and that's going to be found by finding the rightmost function minus the leftmost function. So once again we get a positive value for that. So that's why it's f of y minus g of y. Okay. And then of course delta y once again is the width. And of course our starting and ending points are going to change too. It's not going to be the x coordinates, so the leftmost and the rightmost, like we just did. It's actually going to be the top and the bottom, so it's going to be y coordinates. So we're going to be looking at C and D as where we're integrating to. So basically we're looking at a complete inverse of what we just learned if we want to integrate this with respect to y. And certain functions, it's actually easier to integrate this with respect to y, and this would be a good example here. I mean, these functions kind of go side to side here. They're not top and bottom, but they're left and right of each other. So if we want to find the area between them in this case, we need to essentially integrate with respect to y to do that. It would kind of be nearly impossible to do this with respect to x, because it's kind of hard to draw these rectangles now up and down, because of the way this graph is drawn. Alright, so that's what we're working on here. The same idea, it's just an inverse, right, of what we just did. Okay. So here's the definition. And this is on page 414. So page 414. Alright, so you can follow in the book, but notice that C and D, those are those y coordinates, so that where we're going up and down on the y-axis in terms of our starting and stopping point for our integration. F of y, that's the rightmost graph, and then G of y is the leftmost graph. And then of course when we subtract those, we get the length of those rectangles, and by doing the integration we're essentially just doing Riemann sums much more quickly and efficiently, and adding all of those areas of all those rectangles up together. Okay, so let's try an example here. Alright, here we go. So we've got 23. It's the one that I was wanting to do. So integrate with respect to y. Determine the area of the shaded region in the following figures by integrating with respect to y. Notice we've got two different functions here. We've got y equals root x over 2 plus 1. and then the one on the right hand side is root 1 minus x, and they're both positive roots. And it's also bounded by y equals 0, which is essentially just the x-axis, right? So this one would also be really helpful to actually have this in integrating it with respect to y, because I can essentially just do my horizontal rectangles through here with the Riemann sums pretty nicely and easily. If I wanted to do this one in respect to x and draw rectangles going up and down, what ends up happening is I get a compound region, right? On this side of the y-axis, the top function would be root x over 2 plus 1, and the bottom function would be y equals 0. And over here on this side, the top function would be root 1 minus x, and the bottom function would be y equals 0. So, I could still do this with respect to x if I wanted to, and, should get equivalent answers. One way might be easier than the other. So let's actually work this out in regards to, in respect to y, since that's what they wanted us to do anyway. So the first thing that we're going to want to do is actually rewrite these functions so that they're not solved for y, so that they're actually solved for x, right? Since we're basically doing the inverse of what we just did. So that's the first step. So let's do that. Alright, so this is 23 on page 417. Alright, so the first function that we're given is y equals positive root x over 2 plus 1. So let's solve that for x. So I'm going to square both sides to get rid of the root. Minus 1 then I'm going to times 2. Right, and so now we have this function solved for x. Okay. I'm going to do the same thing for the other function. So y squared equals 1 minus x, so square both sides. Subtract the 1. Divide everything by negative 1. So we end up getting that function. Okay, and then I'm just going to label this which one's the leftmost. So this is the leftmost, and this is the rightmost. Okay, so basically we just rewrote these functions so that they're solved for x, right? Since we're essentially doing the inverse of what we did earlier, so we want to rewrite those. Okay. And then at this point, right, I need to determine my value for c and d. So if we look at our graph again on 23, right, c and d is going to be the y coordinates, so basically the bottom and the top in terms of starting and stopping, right? So I pretty much already know this is 0, so I got that part. Right, so I need to figure out what this value is here. Okay, so I can actually use either of those functions to figure that out. Right, if I know that this point here has an x coordinate of 0, so if I plug 0 into either of these functions, that should tell me what that point is. So if I plug 0 into here, I get the square root of 1, which is going to be 1. And then same thing over here. If I plug 0 in for x here, 0 divided by 2 is 0. Plus 1, square root of 1 is 1 as well, right? So that's how I came up with this value of 1 here. Is I knew that this was going to have an x coordinate of 0, just looking at that graph, so I plugged that in to find the y coordinate. So that gives me my value of C and my value of D. So let's go back over here to my notepad. All right, I'm just going to write down the area between two curves with respect to y, and then we'll match up what we have, C, D. Right, this is f of y, not f of x. That's why we had to rewrite these in terms of x here. So that's why we did that. Okay, so we have C, which is the lower boundary, which is 0, and we have D, which is the upper boundary, which is 1. That's what we just identified. Right? We want f of y to be the rightmost function, right? Which we have already labeled up here. Right? That's the y equals root 1 minus x. Of course, we rewrote it. Solve for x so that we get f of y. So that's negative y squared plus 1 minus g of y, which is the leftmost, right? Written solve for x so that it's g of y. So we've got 2y squared minus 2. And of course, I guess I should include that grouping symbol, dy, right? So that's our integral that we want to try to figure out. So let's simplify some of this, make this a little bit easier on ourselves. So negative y squared plus 1, distribute that negative through, combine those like terms. So we're really looking at this. That looks a lot nicer. Okay. So integrate that. To our fundamental theorem of calculus. So plug in our 1 here. Plug in our 0. So we end up getting 2 minus 0, which equals 2. So that would be our area. All right. So we have found the area between two curves, both with respect to x and both with respect to y. Okay. So let's see, there was one more example I wanted to do here, just to give you guys a plethora of examples to go by. Alright, so let's look at 27. Okay, so here's the directions. I'm on page 418, number 27. So like I said, we can solve these problems both in respect to x and respect to y. And as long as we do all of our work correctly, we should get, an equivalent answer, right? So let's actually start with in respect to y. So if we're looking at this in respect to y, then we're drawing our horizontal rectangles here. So we want to find our C and our D, our lower and our upper boundary. Okay, we want to identify what the rightmost and the leftmost function is. Okay, so we know that our lower boundary in terms of our y-coordinate, that's 0. Okay, so that works out pretty nicely since it's going to stop here. So we know that's 0. We want to find this point, right, to find the lower boundary. So this is the upper boundary, 0. Right, what's the lower boundary there? And of course we can figure that out by setting these two things equal to each other, right? Figuring out what this intersection point is. So to do that, we can set those two functions equal to each other and then of course solve. So subtract the x over, factor this, so x equals 2, x equals -1, right? So those are the two intersection points where those two graphs intersect. So obviously this point here is going to be the point 2, which we do not need. And then this point down here is going to be -1, which we do need, right? And of course I need to plug that in to either of these functions, right, so that I can identify what the y-coordinate is. Well, if I plug -1 into here, right, -1 squared is 1, minus 2 is -1, and obviously plug it into here, -1 equals -1. So this is the point -1, -1. So -1 is not only the x-coordinate, it's also the y-coordinate. So that can be a little tricky there. Trying to eliminate this glare here. There we go. That's a little better. Okay. So we need the y-coordinate, so just be careful of that. Okay. All right. So that gives us C and gives us D, right? So we know that this is the rightmost function, and then the red line is the leftmost function. So we want to solve both of those for y, and then we can write our integral. So okay, so the rightmost, so I'm just going to function is y equals x, and of course that one's easy to solve for x. It's already solved for x, right? Y equals x or x equals y, however you want to think about it. Okay, the leftmost function is the quadratic, which is y equals x squared minus 2. Okay, so we want to solve that for x, so we get y plus 2 equals x squared, and then we root that. Okay. Alright, and of course that's got a positive and a negative root. Okay. And so now we can write our integral. Okay, so the area from C to D is -1 to 0. Okay. And our rightmost function is y minus our leftmost function, and we're actually going to use the negative root here because this is going to be below the x-axis. So negative root y plus 2 dy. So in the problem, it actually just said set up the integral. It did not specify for us to actually evaluate it. So that's what that would look like if we actually wrote that in terms of y. So in terms of y. Okay. If we wanted to do that same problem in terms of x, okay, we would look at this a little bit differently. Okay. So let's go back to our graph. So if we're going to do this in terms of x, we're actually going to look at doing, vertical rectangles, and we are, using our a and our b as essentially our starting and stopping point. Okay, so we need to actually look at this as a compound region. Right, because we actually have a switch as to which function is top and bottom here. Okay, so the region actually gets split right there on that line. Right, so if I look at this leftmost part of that region, the top is the line y equals 0, and the bottom is actually the line y equals x squared minus 2. And then over here in the rightmost region, the top is y equals 0, and the bottom is actually y equals x. So this is a compound region. So this is one of those examples of where this might actually be easier to do in terms of y, because we do have that compound region. But if we wanted to work this out in terms of x, right, we need to find our a and our b. We know this point already is -1. We found that earlier, so that's good. Okay, and we know that this point is going to be 0. So we basically got to figure out what this is right here. Okay, and of course we can do that pretty easily by finding the 0 values of that quadratic. If I find out where this quadratic crosses the x-axis here and here, right, that's going to give me that value. So if we set that quadratic equal to 0 and solve, then we can find that. So x squared minus 2 equals 0. So we get x equals positive and negative root 2, right? And that is our 2, 0 value. So obviously we know that this is going to be negative root 2 since it is to the left of 0. So then this is negative root 2. Alright, so that gives us our a, our b. We know our top and our bottom functions here. So I think we have enough to write our integral. So let's work this out. Okay, so we have our top function, right, is y equals 0, which is essentially just the x-axis. Alright, and that's the top for both of them. Okay, so for the leftmost region, since this is a compound region, right? So to the left of that vertical line, we've got an a of negative root 2 and a b of negative 1. So that's the x-coordinates of our stopping and starting point. Right? We know that the top function is y equals 0. The bottom function is the curve y equals x squared minus 2. And since